Okay, so here we go on day 3 of the nuclear chapter, um, working with nuclear power. So when we induce nuclear reactions, we have some definitions that we need to worry about. The first one is, what is a moderator? A moderator is materials that can slow down neutrons that pass through them. It can also capture neutrons. A cyclotron is a cyclic particle accelerator that works by changing the electrical polarities as charged particles cross a gap, and the particles are kept moving in a spiral path along a strong magnetic field. So these are just some definitions that we need to go forward. If you still need them up, have the subposit. Otherwise, we're moving forward now. A linear accelerator is when we do it in a straight path. We're changing the polarities across a gap between segments in a long tube so we can accelerate particles down a long tube. This one right here is one in California. It's a very long, straight tube. As we use nuclear fuel, we do get 2 major subproducts and then fission products underneath that, and neutrons, so it keeps going. If we have neutron absorbers, that stops some of them from causing fission to go forward. This is the Large Hadron Collider in Europe that everybody was so worried would create a black hole and cause the end of our world. That's sort of what they're talking about right here. It's very, very big. It goes over, I believe, 3 countries. This is transuranium elements. When it talks about transuranium, it means past uranium. These are all unstable, they're all synthetic, and they disintegrate extremely quickly. And they're usually made starting with a gamma reaction. All right, so I'm going to leave this up for a little bit. I'd like you to go ahead and write these down just on a piece of paper. Just grab out a piece of paper and practice writing these down and see if you can fill in the holes. Remember, the top on one side of the arrow needs to equal top on the other side of the arrow. The bottom on one side of the arrow has to equal the top bottom on the other side of the arrow. And then for 9 through 11, you're actually writing the whole equation. It's given to you in words, some of it, and you need to finish writing it. So what I'll do is about every 30 seconds, I'll put up an answer. So go ahead and start with number 1, writing it down. Sorry, I got a little behind here, so I'm putting a bunch up. Give you a few more minutes for 9 through 12. Okay, so I'm going to put the answers up, check and see how you did. Should be about done. Give you a few minutes. If you need the sub to pause this, please do. Okay, we're going to go forward. So as we talk about nuclear energy, we're talking about nuclear fission, and that is a process in which a large nuclei like this is split into smaller nuclei like this, and you're usually bombarding it with neutrons. There's other things you can bombard about, but most of the time it's neutrons, and you're getting off other radiation. A chain reaction is where one thing starts it and it just keeps going and going and going and getting bigger and bigger. Causes repeats. We have two different kinds of chain reactions. One is an expanding or branching chain reaction. Whoops. And that is a reaction in which the products of one reaction cause more than one reaction. And then we have a critical reaction, which is going from just one repeating controlled reaction. It doesn't make more and more and more like the branching tree here. When we have a supercritical reaction, what's happening is it's a branching chain reaction, meaning it goes over and over and over and over and over. Critical mass is basically considered the minimum amount of fissionable material needed for a chain reaction to keep at a constant rate. So that's more like this, where it's just creating one, keeping it going kind of thing. A supercritical mass is the minimum amount of fissionable material that causes a branching chain reaction to occur. So one that will actually branch and do more than one thing. Okay, when we have a breeder reactor, basically what we're doing with a breeder reactor is we start with uranium-235 and uranium-238. It doesn't need to be in liquid sodium. There's other ways that you can do it, but you have a reactor core. And that reactor core creates will create energy, but it doesn't undergo spontaneous fission. It is with elements that will spontaneously, but most often you want to start it with a neutron. You want to be able to start it with a neutron. So you can sort of see the reaction that's going forward up here, how it starts with uranium-238, and then it makes a daughter, uranium-239, the parent is 238, and then the daughter becomes the parent, makes neptunium-239, which is a daughter, then becomes a parent, and it just keeps going down and down and down. So we're going to watch this nuclear reactor video. So pause this video, start that video up, and then come back to this one. Okay, so you should have been able to see how a nuclear reactor works on a very simplified scale. Let's go ahead and look at another video, and where you actually get to see inside an actual nuclear reactor. So go ahead and stop the video and start this video. Or I should say pause the video. Okay, you should have had a chance to look at that. I hope that made more sense. Let's talk about some thermonuclear reactions. These are reactions that require very high temperatures to start. This would be like a nuclear bomb. The sun is one. They just need very, very high temperatures to continue, not something that you want to be around when it actually happens. When we talk about nuclear fusion, we're actually taking two smaller things and making a bigger thing, and we get a lot of energy off. These are the nuclear thermal reactions. We usually get some radiation off too, so you have two smaller atoms making a large atom and a lot of energy. The problem with nuclear fusion that we have is that we can't contain that energy. Try controlling a nuclear bomb as it goes off. It's almost impossible. So we would like to be able to harness that, but we haven't been able to do that. At one point, the U of U thought they had cold fusion, but that was found to be proven incorrect. What I'd like you to do now is stop the video, and I want you to listen to this next video on chemistry. Your health is irradiated food safe, and then come back to this video. Okay, hopefully you realize that it is safe, and it helps destroy pathogens and helps significantly, doesn't significantly affect the nutritional value of food. And it's better that we don't have E. coli in our food system or chemical fumigation to make our food safe, because the irradiation just goes right through the food and just kills the bacteria. We do need to talk about the this is in your book. You'll need to make sure you take it out and read it. But basically, the do's and don'ts of buying prescriptions online. If there's a fail-safe, like we have in the U.S., where if you buy from a U.S. company, they have to follow certain regulations, then we know drugs are brought up to a certain standard. If you buy it outside the U.S., they are not necessarily up to those standards, and so we have a little bit of an issue. You could end up having sugar pills that you're paying several $100s for, thinking they're something else. Okay, so that is the end of today. So what I'd like you to do is make sure that you take time, get your quizzes up to date, redo your quizzes if you need to, work on sapling, and then we'll see you next time.